my camera is turned off
I
automatically. I don't
see.
know. Because of that, you have to see my room. What a pity.
Anyway, Prof. Okay, so it's 7:57 right now. So why don't I introduce speaker for today. So everybody, Assalamualaikum. Good evening. X Shambler, if I'm not mistaken. Is it correct, Prof? The pronunciation X Shambler?
What?
X Shambler. Is it good evening or the
İyi
pronunciation
akşamlar.
is off?
Yes, iyi akşamlar.
X Shambler.
Yes.
Okay. All right, everybody. So we have here today with us is from Cihan Parlak from the physics program, Faculty of Arts and Science, Bolu Abant Izzet Baysal University, Turkey. And also with us here is Dr. Suhadir Shamsuddin. He's from the Faculty of Applied Science, University Tun Hussein on Malaysia. And me myself, let me introduce myself. My name is Saifful Kamaluddin bin Muzakir. I'm from the Faculty of Industrial Sciences and Technology, Universiti Malaysia Pahang, Al-Sultan Abdullah. Such a lengthy name. Anyway, and I have here with my PhD student, Mr. Mirza. And furthermore, Prof, we have students from University Malaysia Pahang, Al-Sultan Abdullah as well, and students from University Tun Hussein on as well. So we have how about around maybe over 30 students. We are expecting more to come after this. So they are preparing for themselves. And everybody, the title of Professor Jihan's presentation today is, let me read, Computational Superconductivity using Density Functional Theory. So this is a part of simulation work. Prof. Jihan will share with us about his work on simulation or theoretical calculations based on density functional theory. If I'm not mistaken, you are using the Abinit software, right, Prof?
Ability software. Yes.
Abinit. Yes. So it's a open source application.
Yes.
So open source application is a freeware. Uh, some of us we are taking the solid state physics and also superconductor in this semester for people from the UTHM, and for my students in University Malaysia Pahang, they will have a class tomorrow morning, which they are conducting virtual experiment using the DFT as well, density functional theory. And one of the experiment is calculating the redox potential of electrolyte, and another group is calculating the multi-exciton generation using DFT calculations. But we are not using the Abinit. Instead, we are using the paid version of the Gaussian 09W. So
Yes.
anyway, Prof, so if you are ready, you may share your slide, and please, the floor is yours. Or if you want to introduce yourself first, so please go ahead, Prof.
Yes. I will share my window now. Is it okay?
Yes, we could see the presentation now.
Okay. Whenever you want, I can start.
Yes, Prof, please.
Okay. Firstly, I am Cihan Parlak from Abant Baysal University, Bolu, Turkey, as Professor Saifful said. And thank you for them to invite me to lecture. I am a bit excited because I never present something last 10 years. After 10 years, it's my first presentation. Maybe I'm excited. Even I am professor. Sorry for that at the beginning. I hope I can this lecture will be useful for you. And today I will talk about computational superconductivity with density functional theory, and outline of my talk like that. I will give a small general information about Turkey, Bolu, and Bolu Abant at Baysal University, our physics department. Then a bit I will talk about basis of density functional theory, small informations about superconductors, and theoretical background of the DFT superconductivity, and little information about Abant software, and our last calculations with Abant software on a superconducting material, and it will be concluded with a small conclusion. As you know, I am from Turkey. Turkey is between the Europe and Asia as a bridge, and we said that Turkey where the continents meet, and we are bridged between the two continents. And Bolu is the small city, as you see in the map. It's a small city in the Western Black Sea region. As you know, maybe
Prof, excuse me, Prof. I hate to interrupt you, but your slide froze just now. Do you have a specific slide for the introduction of Turkey and Bolu?
Yes.
Because we only could see the first slide.
Oh, how about now? Is changed?
No, Prof. We only could see the first slide only.
Okay, just a moment. I will fix. Is it okay?
Not yet.
Not yet. Maybe Prof can unshare and share again.
Yeah, Prof. Maybe you could unshare and reshare again.
Okay. Maybe it's because of the connection problems with Teams. Just a moment.
Sure.
What about now?
Nice. Clear.
Is it work?
Yeah, it's working. Good.
Okay. I hope it's work again. Sorry for that. As you see in the map, Bolu is the small city in the Western Black Sea region, and it's near our capital Ankara. Bolu located between the biggest city of us, Istanbul, and the capital Ankara. As I said, it's a small city, and our city covered by the forest about 60%, and some beautiful lakes around the city. Some of them Saifful Naus, as Gölcük, Yedigöller, and Abant. It's as I said, it's a small city, but it's a very beautiful city, and our university near the city about 7 kilometers away. And we have some historical cave houses and Ottoman houses not far from the Bolu city center. It's town Gölcük, and we have a ski center near the Bolu, we called Kartalkaya, and our traditional food is a pasta, and we call it
Prof, I think your slide froze again. So I believe that you are showing the traditional food right now?
Yes.
Okay. Or if you have the slide right now, can you send, if possible, can you send through WhatsApp to me? Then I let my student, Mr. Mirza, help you to control the slide. It will be okay?
Okay. I will open WhatsApp. Just a moment.
Sure, Prof.
Maybe it's a connection problem. I didn't understand what I do.
Maybe. Mr. Mirza, will you be okay to control the slide for Prof. Cihan?
Okay. I send it to you.
Okay, Prof, I got your slide already. I'm sending the slide to Mr. Mirza. So, Mr. Mirza, please help Prof. Cihan, yeah, throughout the presentation.
Okay, will he share my
Yeah, Prof.
presentation?
So you need to unshare the screen and let Mr. Mirza share your PowerPoint slide.
Okay.
Okay, then so everything good?
We
Okay.
could see. Okay, nice. So straight away to the traditional food. Oh, the
Yes,
foods
it's
are
the
lovely.
Yes.
Yes,
okay.
that one.
Okay, okay. This is our traditional food. As I said, it's a pasta. We call this keşli cevizli makarna, pasta with walnuts and dried salty yogurt. And I think it's the delicious pasta type ever. And if you look the, oh, sorry, next slide, please. Okay, this is the, if we looks the university, it's a state university funded with the donations of the late Izzet Baysal. He's on the picture, and we have about 35,000 students, more than 1,500 academics, and 16 faculty, 1 college, and 8 vocational school. And you see our main campus covered by the oak forests near an artificial lake, and our science and art faculty located here. I'm talking from you, from this pictures building. What a pity I cannot show you with my mouse. Next slide, please. Okay, this is the part of our physics department lecturers. We have 21 lecturers and 12 research lab, includes scanning electron microscopy, X-rays, and sputter, and some cryostat systems for mostly for condensed matter labs. And we have 8 undergrad student laboratory. And next slide, please. General research areas in the physics department like that. We have a group we study with high energy physics. They make phenomenological calculations about high energy, and they have some CERN partnerships. We have 2 lecturers for nuclear physics, but I don't know what they do. And most of the lecturers in the physics department study solid state physics in these areas: computational solid state physics, bulk, wire, and type superconductors experimentally, and semiconductor, LED, and sensor applications as semiconductor physics, and magnetic materials, mostly studied in physics department. And 3 of our professors work on quantum information, quantum entanglement, and quantum thermodynamics, and all general subjects that we talk in physics department in Bolu like that. And one more slide, please. If we start to scientific work a bit, what is the density functional theory? Density function theory is one of the most popular and successful quantum mechanical approach to solids, which developed by Walter Kohn. He was awarded with the John People the Nobel Prize in Chemistry in 1998. Maybe you know it well. And next. Okay, why we need to density functional theory? If you want to do some quantum mechanical jobs with computational area, we have to solve a many-body Schrödinger equation, and with the aid of the von Oppenheimer, we can divide this Schrödinger equation with cores and the electrons, because of the, we can say that cores are the heavier and relatively stationary, but electrons are the moving. And even we decouple this equation, it's huge terms because of the many-body. Really, it's many-body. Schrödinger equation has many-body term for real materials, and it's hard to solve this with numerical or analytically. Analytically maybe impossible. Next slide, please. Why it's hard? It's a small example. Just if we take the carbon monoxide molecule, it has 6 plus 16 electrons, and all electrons has 3 spatial coordinates, and our Schrödinger equation becomes 66-dimensional problem, even a small system. We have only 3 atoms, but it's hard to solve such things with analytical or numerical way. And next slide, please. As I said, unfortunately, the solution of this equation cannot be found in neither analytic nor numerical form because of the Coulomb term in Hamiltonian, with couples all the electronic degrees of freedom. And for this reason, it's convenient to shift the interest from many-body wave functions which solve the Schrödinger equation to the ground state electronic charge density, which allows us all the same the computation of the physical ground state observables. Indeed, in practical calculations for Schrödinger equation is replaced by the equation derived by density functional theory named Kohn-Sham equations or Kohn-Sham. Next slide, please. And if you look at the Kohn-Sham equations, it looks like a Schrödinger equation, but as we said before, we changed the spatial coordinates with the electron density. Here we have an kinetic energy term again, and Hartree potential, exchange correlation potential, and external potential. Exchange correlation potential, we don't know this potential exactly. Roughly, it's mostly approximated from electronic density of states of the electron guts with some Monte Carlo simulations. As I said, we don't know the exact value. We approximate this potential. The Hartree potential is actually a classical Coulomb potential for electron densities, and external potentials describes the effect of the nuclei plus in case external forces as electric field if there is any perturbation, and we calculate the density as the classical quantum mechanics, the expected value of the Kohn-Sham orbitals or wave functions. Simple exchange correlation functionals are local density approximation and general gradient approximation. I will not give much details about these ones. Maybe you are some of the physicists familiar with this because of the computational area. I didn't see the slide on the screen.
Mr. Mirza is resharing the slides. Yeah, okay. Okay, now we could see the slides.
Okay, next slide, please. Okay, if we change the Schrödinger equation to Kohn-Sham equation to our system with density, electron density, Kohn-Sham equations can be solved in a periodic solid expanding the Kohn-Sham orbitals or wave functions in a complete set of noun functions. Noun functions can be Gaussian for molecules, but the best choice or the easiest choice is the plane waves for the crystal structures, and mostly crystal structure calculations prefer the plane wave basis. It's easier to do periodic with the crystal periodicity, and this potential is periodic with the same periodicity of the Bravais lattice of the solid. The potential is the Kohn-Sham potential. As I said, includes three terms: external potential, Hartree term, and exchange correlation potential. And here we can use the Bloch's theorem and blah blah for the solution for these Kohn-Sham equations, and directly, as I said, because of the periodicity of the lattice, we can connect the plane waves periodicity easily. We can connect these two things, and we can solve this equation with a plane wave basis for periodic structures. But you don't need this if you have just molecule. You can use only Gaussian wave functions for only molecules. Next slide, please. And how can we define the plane waves for this system? Still, we have some problems if we use plane waves for all electrons. It's really expensive for CPU time. Because of that, we have some theory, maybe pseudo potential. We can replace the effort of the core electrons are smooth in the core region with like as you see in the red, pseudo potential or pseudo wave function, and reproduce all electron potential behavior out of the core region. RC is the cutoff radius. It's far from the core of atoms, and our potential is the same with real potential, but left-hand side, at the left-hand side of the cutoff value of the distance from the core, we find a new potential. If we solve this potential, or if we simulate this potential with the plane wave basis, reduction of the number of plane waves we need, but we can choose, we can find the physical meaningful values again. And one more useful things, when you use the pseudo potential, the number of the electrons will be decreased, because we will just take the valence bands in our calculations, and reduction of the number of bands for solve our code. And our code is used the pseudo potential, and there are many types of pseudo potentials, or like pseudo potentials like potentials. The well-known are non-conserving pseudo potentials and ultra-soft pseudo potentials. Next slide, please. If we have pseudo potentials, a DFT code, And what happens here? We take pseudopotentials of atomic pseudopotentials, and we take these values and create an initial electron density for our system. Then we solve our calculate the effective potential firstly, then solve Kohn-Sham equations with that effective potentials, then calculate the electron density again. Is it self-consistent or not? If it's not self-consistent with each other, starting electron density with the last electron density, if not self-consistent, we change the our guess and do this cycle again and again. After that process, we will get the self-consistent electron density, and then this means we get the true ground state of energy. As you know, we can get the energy eigenvalues from the solution of the Kohn-Sham equations as Schrödinger equations, and then we can find the energies, forces, stresses, and we can do geometry optimizations with the forces or the minimizing energies, and further on we can use this ground state energy for density functional theory, perturbation theory, or linear responses, and we can calculate phonon frequencies, dielectric constants, or elastic constants, and more with the starting point from here, and go on with the one step more complicated calculations as density functional theory. Next slide, please. After our basis of the density functional theory and pseudopotential theories, and maybe everybody knows what is superconductivity. Superconductivity is a set of physical properties observed in superconductors. Superconducting materials where electrical resistance vanish and magnetic fields are expelled from the material below the critical temperature. In the red line, as you see, after a critical temperature, resistivity of the metal getting really zero and no resistivity after that line, but it's not seen in the normal metal such behavior, and we will deal with so next slide, please. Okay, this is the historical chart of the superconductivity, and the superconductivity found in 1911 by Ons for mercury at the 4 Kelvin, and then we found a lot of superconducting material, but we are looking for the room temperature superconductivity. The aim of these studies, can we found any miracle material show us the superconducting properties at the room temperature. At the 1985, the big step that found the copper-based superconductors. Other breakpoint founding MgB2 as a superconductor at the beginning of this century. Maybe you know, Nagamatsu found the MgB2 superconductor, and after that a lot of studies, a lot of MgB2 like materials studied for physicists. Next slide, please. And as a result, within today's technological applications, the most used superconductors are simple intermetallic alloys. As you see, some of them in the last slide. And now most of the physicists try to high pressure studies to catch the room temperature superconductivity, they use some really small superconductings with the diamond oval cell and show the superconductivity under really high pressure as more than 100 gigapascal, and hydrides, very popular in these days under pressure calculations. But for technological applications, we still use simple intermetallic alloys at the TC about the range 1 to 30 Kelvin. In addition to being much cheaper and easier to manipulate these superconductors, unlike the exotic copper-based superconductors or high-pressure studied superconductors, an ab initio method to calculate the electron-phonon coupling in last 20 years is such that the normal and superconducting state properties of actual materials can now be computed to high degree of accuracy based on the soul of the knowledge of the chemical composition and crystal structure. If you have just crystal structure of solids, you can easily pound the ground state and more accurate superconducting properties, and we have get the great accuracy with respect to experimental one, and the disciplines approach adopts an appropriate formula for critical temperature. The two main things we talked in DFT superconducting mostly. One of them, electron-phonon coupling constant. It comes from the BCS theory, the old theoretical explanation of the type 1 superconductors, and this is the very effect on critical temperature electron-phonon couplings. And most of the codes and very popular calculations use the Allen-Dice modified Macmillan equation. We get the, if we can calculate the phonon frequencies, we can calculate the logarithmic average of the frequency and electron-phonon coupling constant, and then we can get the TC values of a superconductor with the aid of the density functional theory. As I said, we need to only crystal coordinates and crystal composition of the system. We can calculate the critical temperature. We don't need the expensive experiments most of the time. If we just want to see is it superconductor or not, we can calculate maybe. Okay, next slide, please. Okay, as the Professor Saifful said that we use Abant software. Abant software is the suite to calculate the optical, mechanical, vibrational, and a lot of other observable properties, starting from the quantum equations of density functional theory, and you can build up to advanced applications with perturbation theories based on DFT and many-body Green's function and dynamical mean field theory. I don't have any experience about green functions and dynamical mean field theory with Abant. You can
Prof.
easily...
I believe
Yes?
Dr. Su raised up his hand. Maybe he has a question, I believe.
Yeah.
Yes.
Maybe during we can interrupt some question and answer. Can
Yeah.
Prof?
Which one?
I'm interested about the previous slide, Prof. The previous slide.
Yes.
Okay. Okay. Very good morning, Prof. I'm Dr. Suhadir. Okay, from UTHM. Okay.
Okay.
Actually, Prof. Actually, my background and my expertise is I'm preparing superconductivity. I'm preparing a few superconductor, thallium 1212, YBCO, and also viscose superconductor. And,
Experimentally?
yeah, experiment, Prof. And
Okay.
then experiment. Okay, and then I also playing with some magnetic materials like cobaltates and also manganite related to the CMR material. So during your presentation, I believe you mentioned that you can prove the behavior of the superconductor by using the DFT, right? By determining the critical temperature, right, Prof?
Yes.
Yeah, I'm not familiar about the FT one, but I believe I'm measuring the superconductor experimentally. I'm characterize for example the thallium 1212 sample, and I was get the critical temperature around 100 something Kelvin, and it's by experiment. Okay, and then how this DFT can help by only calculating the, I don't know, the electron phonon coupling, and then I also discuss the electron phonon coupling, something like related to Jahn-Teller effect. Okay, and I believe I'm very interested with this one, Prof. So maybe you can a bit explain about how the FT can approve by calculating the electron phonon coupling, we can get the value of the critical temperature.
Oh, as I said, we Abinit code use the density functional theory and linear response that allows to calculate phonon frequencies.
Well,
And if you the the below one, if you calculate the phonon frequencies and logarithmic average of them and take these logarithmic average values at the TC formulation,
yeah,
it's not too complicated if you have time and enough CPU. Maybe
okay,
hard to explain. How can we calculate this? We cannot do that in hand, by hand, I think,
yeah,
because of the huge computation you need for that. But as I said, it's not too different from the calculating phonon dispersions.
yeah, yeah.
Uh,
The, yeah, that
if
is,
you need to calculate phonon dispersions, uh, you have maybe a lot of way, but you have two popular way. One of them, frozen phonon, that the VASP code calculate frozen phonons for
yeah,
phononic
yeah,
calculations or phonon dispersions, or I will give some references for such things at the end of this slide, or you can use density functional theory as Abinit. If you make a if you give the position, the perturbation to atoms, and you can calculate the response of your lattice with the relatively total energy. You can calculate the phonon frequencies. If you
okay,
calculate the frequencies, you can calculate the
yeah,
TC values.
okay, all right.
Maybe
For the
maybe
information,
hard to explain on the web, but I will give you an detailed reference for this one at the end of the slide.
okay, thank you very much, for because before this, I also doing the experimental using what we call that ultrasonic velocity measurement. So we are measuring the wavelength, okay, the frequency also. So we got some reporting the behavior of the elasticity at lower temperature measurement, and then we just saw some anomaly behavior. So
Yes.
yeah, anomaly behavior. So and then some we only discuss it related to Jahn-Teller effect and related to the electron phonon coupling, but we can prove that by the some value of calculating. So I think this is can be possible. Okay.
Maybe you can mail me after that. Maybe we can discuss about that. I
Sure.
cannot. I don't understand exact problem of yours, but maybe we can get a middle
Yeah.
way between us. After that, you can mail me if you need.
Sure can, bro. Because during your presentation, I was very interesting a few terms on superconductor, because I'm teaching this superconductor almost 7 years. So this is my opportunity. Okay. So discuss with uh I think expert on superconductivity also and DFT from Turkey. So thank you for giving this kind of opportunity, bro.
Oh, I thank you too.
Okay,
Okay,
Prof.
Proceed.
let's go to next slide, please.
Sure.
Okay, in my mind, as I said, you can. It's open source code. You can download it www.abinit.org or RG, and it's a Fortran code. You can easily, sometimes not easily, sometimes easily, can compile that code with iFort, Intel Fortran compiler, or G-Fortran. It's open Fortran compiler too. And you can be parallel this code with MPI or OpenMP. Sometimes it's complicated job, sometimes it's not. Some versions you can easily compile, but sometimes you cannot easily compile this code. Most of the time you need the experience to compile such codes, as you know. Abinit is not one of the best code. You can also use open source Quantum Espresso, or not open source, WASP. WASP is the popular one, but it's not cheap. And next slide, please. And Abinit use norm-conserving pseudo potentials, or you can use projected augmented waves for your some calculations, and you can download required pseudo potentials from the pseudo dojo website, as I given in the below. And non-conforming, a lot of non-conforming potentials has there for about all periodic table. When I was young, it's not possible. We generate most of our pseudo potentials by OPM code or a code from the Germany. I didn't remember the name, but new students are lucky. A lot of pseudo potential set we have on the web, open software, and pseudo dojo Abinit support these pseudo potentials, and Abinit website suggests you this kind of pseudo potential sets, and you can download other atomic pseudo potentials from here, and you can start your Abinit calculations. Next slide, please. Here a example input file for Abinit. This is the geometry optimization file. We have two data sets. At the first data sets, at the line 5, we optimize just internal coordinates at this first step. You can optimize the full geometry in the beginning, and you can do only one data set. But if you if you want to make shorter calculations, this is the best way. Maybe firstly you can calculate the internal coordinates with IOMOV2 keyword. In the website of Abinit, you can get from Abinit tutorials and the keywords that you need, and some convergence criteria. The second data set, we do full optimization, internal coordinates and the volume optimization of our cell, and related criteria given in that. And the right hand side, the general informations for our lattice. We will calculate the calcium diboride. Looks like magnesium diboride. I will say to you why we want to calculate calcium diboride, and we give the cell parameters. This is not maybe you know, this is the just suggestion for lattice parameters A, B, and C parameters. You can take this from an experimental results, or you can just take the random values, and angle between these lattice parameters are 99 to 220 to determine the hexagonal lattice one, and the atoms where X-ray keyword show you the at the 000 point we have a calcium 1/3, 2/2. 1/2 is the boron 1, and 2/3, 1/3, and 1/3 the second boron. And we have two type of atoms. Total number of atoms is 3, and atomic numbers, one of them calcium 20, one of them boron is 5, and the other sections, it comes from the DFT convergence, cutoff energy, the meaning of the how we take the plane wave expansion, take long or short. If you make short energy cutoff as more than 40 Hartley, accuracy is the better, but CPU time is very expensive. We have to optimize that. I will show you in the next slide, I hope. And at the below of this input file, give the pseudo potential informations. You need calcium and boron pseudo potentials. As I said, I use the pseudo potentials downloaded from pseudo dojo. Okay, next slide, please. Okay, now I want to represent an example calculations of us. Why I show you that, as I said, the breaking point of the studying superconductivity founding of the MgB2, and after the discovery of MgB2 is a superconductor by Nagamatsu, a lot of type of MgB2 is the hexagonal structure, and we call this one is the aluminum diboride type. And if you want to find any new superconductor in the this hexagonal form, you can try to find another, and you can change the magnesium, or you can change the borons like galliums like that. And a lot of study on this type aluminum diboride type materials already published. And why I choose the calcium diboride? Calcium diboride is the hypothetical, still hypothetical. There is no experimental results on calcium diboride, and calcium diboride also you can it can be crystallized in the aluminum diboride structure. But if you look at the calcium boride structures, you will see the calcium hexaboride mostly, and it's also a superconducting material. Maybe it's hard to synthesize aluminum diboride type hexagonal calcium diboride. Maybe easily system move to calcium hexaboride, and you can go to, when you try to find calcium diboride, you will get the calcium hexaboride. I don't know the experimental steps of this, but it's hypothetical for now. And next slide, please. Okay, if we do a geometrical optimization, we can calculate the structural parameters of this hypothetical hexagonal structure, and we use both GGA and LDA exchange correlation that I told in the DFT section, and our calculations very similar with the other calculations. As I said, I cannot compare these values with any experimental results. And when we do other hexagonal structures, I can say that these optimized lattice parameters is the very true. And and as we see, as we compare the calcium diboride with the magnesium diboride, calcium diboride has the much longer or larger lattice parameters than magnesium diboride, as seen in the slide. Next slide, please. And as I said, first of all, before the after the I do convergence test after the geometry optimization, but sometimes you have to do convergence test before the geometry optimization, or 2 times you have to converge something. Convergence test, you try to find minimum change in the total energy. It's about 0.001 electron volt convergence. If you get, it's enough for you. As you see here, 14 Hartree, Abant use Hartree, and the Bohr. Lattice units are Bohr, energy units is Hartree. If you use 14 Hartree for calcium diboride, you will get the enough convergence. If you converge, if you have good convergence, you can exactly say that your phonon frequencies are the good values. Or if you don't have enough converge your system and use a narrow cutoff energy, you cannot say that the phonon frequencies are true or other physical properties are part of experiment or the harmony in experiment. And second, convergence test for the K-point sampling for Brillouin zones, it's important too. And you can change the K grid. For example, hexagonal one, you can change the values at the z-axis, but I prefer the cubic sampling. I like, just for me, I like that. And 16 K point is enough for this convergence for this material, as you see in the table. And again, we want to converge the energy 0.001 electron volt. Okay, next slide, please. And after the convergence test and geometry optimization, we can get easily bulk modulus values. The important mechanical parameter describes the substance existing pressure, and you calculate the optimized A and C values. You can change the volume slightly, and again you can calculate ground state total energy. And every time you can put these values on the graphics and fit this energy volume values on an equation of state as Muranagan equation state or V-net equation state, you can easily calculate the bulk modulus. Bulk modulus of the calcium diboride is 121.5 gigapascal for GGA exchange correlation, as you see. Next slide, please. And with the aid of the density functional perturbation theory, you can easily calculate the elastic constant. And we have 6 independent elastic tensors in the Young notations. These values are in, again, gigapascal. Next slide, please. This is the not much. Okay, if you calculate the elastic constants, just you need to you can do some analytical calculations for get shear modulus, Young modulus, Poisson ratio, and anisotropy or hardness of this material. And here we give some numerical values for such things, and we can calculate the Debye temperature from the elastic constants calculated by density functional theory. And now we can say that Fuchs index, shear index over bulk modulus greater than 0.5, it's said that calcium diboride is the brittle material. And if you look the universal isotropy, AU, is near the zero. If the universal isotropy is zero, completely your system is the isotropic. As you see, 0.03, it's also isotropic crystal calcium diboride. Okay, next slide, please. Okay, maybe for superconducting calculations, the important parameters, one of the important parameters is the electronic band structure. Maybe you know, we have, as I said before, the BCS theory. BCS theory said that if you want to get good superconductor, you have to find a material that's density of states at the Fermi level should be higher. And as you see here, we calculate the band structure of the calcium diboride. And some theories or some calculations said us, if you want to get good superconductor, your material should be higher density of states at this state at the near the Fermi level. Here, as you see, the green one, the green line is the Fermi level here, and we have p states of boron atoms and these states of the calcium atoms around Fermi level, and 3 electronic band cut the Fermi level, as you see, and 0.198 electron volt over states over electron volt times cell, total density of states for this material we can see. And next slide, please. Okay, if we look the Fermi surface of these 3 Fermi level cutted band, 2 of them whole type p bands Fermi surfaces, as you see here as a pipeline, 2 of them. The third one is the top and the lowest surface of the Brillouin zone, and you can let what is the meaning of these hexagonal points left hand side. I give the high symmetry points. Gamma is the center of the Brillouin zone, and A is the top, M is the lower surface that near looks to us. And next slide, please. if we look to combine of these three bonds, cut at the Fermi surfaces, and the right hand side we have the MgB2 Fermi surface. It's a bit, mostly we can say that it's similar. MgB2 has the cylindrical hole type Fermi surfaces at the center of the beryllium zone, and calcium diboride 2, and MgB2 has the other one Fermi surface at the top and the lowest hexagonal sides. Just one more addition in the magnesium diboride between this top and the lowest side, one more surfaces between the layers. As you see, one more surface, just little difference, I can say that for MgB2 to calcium diboride. Again, next slide, please. If you look at the vibrational properties, phonon frequencies of the calcium diboride, the highest frequency, maybe you know, calcium, as I said, from the input file, calcium diboride has 3 atoms in its unit cell, and because of that, we can see 9 phonon frequencies for that. But two of them, EG1 and AG2, is the acoustic modes that are 0 in the center of the beryllium zone, and other phonon frequencies given in this notation like that. The highest frequency of the calcium diboride is 658 centimeter over 1. It's not higher than the MgB2. This is important because of next slide I will explain why the highest frequencies are important for such materials. Next slide, please. Okay, if we look at the complete phonon dispersions of calcium diboride, and yellow circles is proportion of the magnitude of the electron phonon coupling strength. This means electron phonons couple these areas in the match, and as you see, the highest frequencies around 600 soften in the middle of the beryllium zone. Gamma is the again center of the beryllium zone, and electrons and phonons couples at the about 400 centimeter over 1 minus 1, and the right hand side also the important parameter alpha square f of omega is make a very big peak at the red peak at that phonon frequencies. This means calcium diboride probably will be higher, relatively higher TC values. But if you look this sham for MgB2, for phonon frequencies is higher than calcium diboride, and magnitude of the electron phonon coupling strength is higher at the higher levels, and this means you need to, maybe we can say that you need the higher phonon frequencies, and at the higher levels, if electron and phonon couplings with each other, you can get better higher TC values. Next slide, please. Okay, here some values important for superconducting properties. Lambda, as you know, electron phonon coupling. TC is the critical temperature. As you see, we calculate the critical temperature for calcium diboride about 24 Kelvin, and Debye temperature is 668 Kelvin, around that. And MGB2, if some references values for MGB2 DFT calculations, they calculate the TC as 14 near the experimental value, but electron phonon coupling constant is lower. It's not expected because of, if in normal conditions, we can say that if we have higher electron coupling constant, we have to get higher TC. But as you see here, our calculations a bit higher than MGB2 calculations, but our TC value is smaller than the MGB2. It's probably related to frequencies is very high for MGB2 material. Maybe you read some computational superconductivity. Ashcroft said the best superconductor will be solid or liquid hydrogen, because hydrogen will be really hydrogen is the higher atoms, lighter atoms, and will be show the really higher phonon frequencies, and maybe his opinion, it will be the best superconducting we will see in the maybe next 20 years. As you see here, one of the calculations on calcium diboride, some groups said that calcium diboride will have 15 Kelvin critical temperature. I think not. It will not be. The last calculations on calcium diboride from a Chinese group, it's relatively same with us. The 15 Kelvin calculations of the old one, they take only anharmonic phonon frequencies in their calculations, and they said that calcium diboride will be better superconductor than MGB2, but our calculations and the Chinese group calculations, it's relatively 24, 28. It's relatively same. It will be, we said that if we synthesize the calcium diboride, it will be has lower critical temperature than MGB2. Next slide, please. Okay, we come to nearly end. Conclusion of these results. The hypothetical calcium diboride, as I said, it's not observed experimentally, but when energy calculations and our if you calculate the cohesive energy, it said the calcium diboride can be synthesizable, and our phonon frequencies shows if we synthesize calcium diboride, it will be dynamically stable, and our elastic constant calculations show calcium diboride is the mechanically stable, but for now it's not synthesized, and the value of the debye temperature is about 676.4 Kelvin. This means, and electrocoupling constants, calcium diboride will be relatively high TC if we can synthesize this, and electronic band structure and the Fermi surfaces show us its electronic structure. It is not much different from the MGB2 structure. The difference between the TC values probably will be caused from higher phonon frequencies for MGB2. Next slide, please. If you care about this, I didn't show the much more complicated math for density functional superconductivity theory. A lot of web source, but Lydia Bovary is the famous physicist that study on the high pressure superconductors on computational way, and she write a lot of paper about that, and this is the good source for if you care such things. Understanding novel superconducting with ab initio calculations in references is here. And next slide, please. And if you care about how can we calculate phonon frequencies with the linear response, you can read this paper from Baroni. And Baroni and this group also create the Abinit-like open source software. And most popular than Abinit, Quantum Espresso. As I said, it uses ultrasoft pseudopotentials, but most popular than Abinit. Also, you can read this one, and you can also use Quantum Espresso for this such calculations. All calculations you can do, you can do with Quantum Espresso too in this study. Next slide, please. Okay, because of the time shortages, I didn't give the references of these slides in the slides. You can find the reference values of the other calculations and other references in my recent paper about calcium diboride with that paper. And the end one. Next slide, please. Okay, I will thank you, Dr. Professor Saifful. Maybe you know this guy at the Gölcük, and the handsome one is me, as you see in this photo. Thank you for listening me, and thank you for again invite me, Professor Saifful. Okay.
Thank you, Prof. Cihan. Well, is it okay if we ask a few more questions to you?
Yes.
Okay. Now I have the first question from me will be if we have our output.
First, you will ask a lot of questions, as I see.
No, just few questions only.
You have two questions.
Okay, two questions only. All right.
No. So, I am kidding. If I can, you can ask me whenever you want.
Okay. This question maybe will assist the newcomers. I mean, to try to explore the DFT more. And my question will be, how do we evaluate? How do we know if we are calculating the calculated system is realistic? How do we know that if they are realistic? Is there any indicator saying that, if you calculate this the calculation is around this area, then that will be realistic? And is there any procedure, Prof, to know whether the system or the molecules or the crystals are realistic?
If you have experimental values, you can check the experimental values with your system of, as in my example. If you don't have any experimental one, you have to compare similar materials, or you have to calculate cohesive energy, mechanical properties, is it stable or not, or dynamical properties, is there any negative phonon frequencies or not. If you have negative phonon frequencies in the Brillouin zone, it said dynamically its material will be unstable or metastable. If mechanically unstable from the calculations of the elastic constant, if it's mechanically unstable, probably it's impossible to generate it in the experimental one. But the best way, you have to do experiment.
Yes. That's the best way. Okay. One more question from me. I believe Dr.
Okay.
Suhadir has questions. Well, allow me to ask one more question, Dr. Suhadir. Now, Prof, if we have, I'm a Gaussian user.
Yes.
Some of the function is very user friendly. But one thing that I observed is that I could not map the density of state using Gaussian. So I saw that you presented just now using ABinit, we could map the DOS. So my question will be, can I use the output from Gaussian calculations and open in ABinit and map the DOS? Will that be possible?
I think you cannot do it such way
I see.
because of the density of states. As I said in the Abinit part,
Mm-mm.
for pseudo potentials,
Mm-mm.
step by step we calculate the electronic band structure of our crystal structure. Maybe you can use your molecule in a supercell
Mm-hmm.
with Abinit, and I never heard take the values from the Gaussian and open it the Abinit. It's
Mm-hmm.
impossible, I
I
think.
see.
But maybe, but not. I think Gaussian is not good. Gaussian cannot calculate the density of states. I think maybe
I see.
you can but you can make a big supercell and put your molecules in that cell, and you can find the density of states probably with
Mm-hmm.
Abinit or quantum expressor, I think.
We will try to look into that, Prof. Hopefully, we're aiming for a paper later. Maybe we could discuss furthermore the results and its discussion. So we might need your advices as well, which later we could communicate via emails or WhatsApp.
Yes, it can be better.
Yeah. Okay, Dr. Su, your turn.
Yeah, thank you very much, Dr. Saifful and Prof. Jihan. Okay, during the presentation, I saw many things which very related to me. And then, for your information, Prof, I'm the experimental person. Okay, I'm the experimental person. So I have doing determining the lattice parameter by experiment using XRD. So I'm determining using the SRD, determining the A lattice, B lattice, C lattice, as well as the unit cell volume. Okay, and then conform the structure. I'm play with tetragonal structure, orthorhombic structure also. Okay, so I saw your slide. You determine the lattice parameter by DFT. So I think it's very interesting for me. It's a new information for me. The first one, and then the second one, I also measuring, okay, the elasticity, the elastic properties for certain material. Okay, I'm determining the manganite. I'm not sure if you're familiar with the magnetic material. It's a manganite compound related to the colossal magnetoresistant CMRs, and I'm determining the elastic properties by experiment using ultrasonic velocity measurement, and it give information on longitudinal modulus, Shaw modulus, and then we are calculating the Bach modulus, Young modulus, as well as the by temperature. So I'm quite surprised you determining all that one using DFT. So
Yes.
yeah, so I'm very interesting that, so that I can calculate it my sample and comparing with the DFT. So it's very interesting paper to write it. I'm sure.
Okay, as I said, I am here. You can connect me with my old all telephones and emails has Professor Saiful. We
Yeah,
can connect each other for
that's
about
true.
that too.
Yeah, I think
Sure.
it is the very good opportunity because I'm in the process. Okay, I'm in the process learning the FT with Dr. Saiful, and then I saw this is a big opportunity because you determine how you calculate the TC. Okay, and then for your information, I'm also playing with the magnetic material, which it's measuring using DC electrical resistivity measurement. Okay, DC electrical resistivity measurement at lower temperature using the cryogenic system. And then our sample is, interestingly, it transformed from insulator to metallic behavior. It's my sample. It's called a transition temperature there, similar with superconductor, from conductor to superconductor. But I'm also playing with other material which is transformed from insulator to the metallic behavior, which means insulator to the conductor lah, right? Something like that. So I believe DFT can help to maybe to prove, okay, the behavior of the resistivity at lower temperature. Because I'm planning, I also what we call play with what we call the electron phonon coupling, something like that. So but I'm not familiar about that one because I'm not the theoretical one. So I believe the DFT will reveal, okay, how the electron phonon, how the electron magnon, and something like phonon coupling. Maybe I'm sure it will be a very good opportunity here. So I have Prof. Jihan
I'm
can,
not.
yeah.
I'm not know what about your crystals, but in DFT superconductivity, a lot of type of materials can be studied. Just cup rates a bit harder for DFT for now, but other ones mostly possible.
Yeah.
But sometimes if you have a lot of atoms in your unit cell, it's very expensive for computational time.
Yeah, because my sample, I have a few combination of element. Okay, I'm playing with, for example, currently we are playing with what sample, Tio? This
Playing
is
with the
my student.
presidium, sodium, silver, and manganese oxide.
Okay. Right.
Uh, as I said, let's discuss about this with email.
Okay.
It will be more complicated for students and other audience, and it's hard to and it's hard to communicate here.
Yeah.
My English
Anyway,
level is
Prof.
the low. Maybe it's my English level is the lower. Sometimes I didn't understand what you mean. Because of that, sorry for that.
By the way, Prof, Dr. Suhardi is visiting me soon, around towards the
End of this month.
end of this October, and we will have a discussion first at my place. I mean, Dr. Suhardi's place is at the southern part of Malaysia, and my university is in the eastern part of Malaysia. So we will have a short discussion first. Let's see the IBNIT, also the Gauss view, and also the DFT, and then maybe we could formulate something, collaboration between these three universities, and try to focus on work on something in common that maybe we could have an output sort of like an article paper to be submitted in Scopus or WS Index Journal or whatnot. So let us try to work on our side
Uh,
first.
yes, if I can do some calculations, or if I can help you for your calculations, it's possible. Why not?
Yeah, sure,
Nice.
And next week I will be free of the feed of the department. I will have more free time.
Oh. Should I say congrats or the other way around?
Yes.
Congrats, Prof. So you
Thank
can
you.
do your full-time research after this, right?
I hope if my
Yeah.
children allows me, yes.
Okay, so it's already 9:22 because if we follow our tentative, it's already past 45 minutes, and I believe that our time, our session will end around 9:30. Anyway, I hope this our effort, I mean, our collaboration will not stop here. I believe this is just a beginning of the future collaborations between these three universities. And before we conclude, I would like to extend my heartfelt thanks to Prof. Cihan Parlak for his valuable insights, and also Dr. Suhadir Shamsuddin for his contributions during this session. I mean, we are expecting a three-way partnership. And thank you to the students from the three organizations, from the UTHM, from the UMPSA, also from BAIBU. I believe I saw one Turkish football player name, Furkan Yasa. That is Turkish football player name, right? I believe that is the students from your side, Prof. Cihan?
Yes.
Yeah, okay. Thank you for coming today, for joining the session. And yeah, special thanks to you, Prof, for sharing about Turkey, Bolu, and BAIBU. Well, it actually brings back wonderful memories. I've been there last year. I really truly miss the food in Bolu,
Okay.
and
You're
the conducive learning and environment at BAIBU is very conducive for learning. And what else? To all participants, may I kindly request you to turn on your cameras for a group photo to capture this, I mean, this very memorable moment. So please, everyone, turn on your camera.
Will you send me this photo?
Sure. Sure, Prof. The photo and also the recording of the session as well. I will send to you. So everybody, please turn on your camera. Mr. Mirza will capture this moment. Mirza, give us a hint if you want to capture the moment, yeah? Sometimes we forgot to smile, so make sure we are in the best form for you to capture the picture. So everybody, please turn on your camera with Prof. Cihan. So you are counting down, Mirza?
We need to wait everyone to open, or
We give 10 seconds. How about 10 seconds? 10 seconds for them to turn on their camera. Maybe they are adjusting the awning of their scarf, or try to powder their face. Who knows? So everybody, please turn on your camera. This is a very rare moment. Some of my students said that Prof. Cihan's face really looks like Clint Eastwood. It's a famous actor from the US. Okay, Mirza, 10 saat dah? 10 second done?
I think it's okay.
Okay, now, okay. Let us know.
Okay, some people cannot open the camera. Okay.
It's okay.
Okay, 1, 2, 3. Okay, one more time. 1, 2, 3. Okay.
Done?
Okay, done.
Thank you very much, Mr. Mirza. And once
Thank
again,
you very
guys, thank you to everyone for your active participation and engagement throughout this session. Don't feel bad if you don't understand. At least you are in the discussion of advanced knowledge we are talking about. So maybe this is your turning point to go into deeper knowledge in physics. And it's been a privilege to share this learning space with all of you. I mean, let us try to continue fostering connections across border like this, Malaysia, Johor, Pahang, and also Turkey.
Yeah.
And yeah, keep the spirit of learning alive. And I'm wishing everyone success in your future endeavors. With that, we officially conclude today's session. And thank you. Have a great evening ahead. Thank you, Prof. Cihan. Thank you, everybody.
Okay, thank you.
See you again soon.
Dr. Saifful.
Yes, thank you.
Sambung program lain pula.
Thank you, Prof.
Okay. So, Prof, we are having, I mean, a short discussion within the UTHM and UMPSA. Thank you again, Prof. We'll invite you again later soon for our next discussion.
Okay, I will close the.
Yeah, thank you, Prof.
So thank you.
Thank you.